Oh, sound check. What channel are you on, A or B? I'm on B. Try B again. You have me? Okay, I'm on B. All right. Cool, yeah, switch it. You try A when I try B. All right, welcome, welcome, welcome. Grab one, pass it around. Grab one, pass it around. And grab one, pass it around. All right, well, it is 5 till. I got a couple things going around and get us started. And welcome back. Good to see everybody. I know that you've probably been spending all summer anticipating coming back and probably missed the wonderful opportunity of doing homework late into the night and studying for tests. And it's back, believe it or not. And we're ready to get started and to switch gears to a new topic. And we are going to do electricity and magnetism. And since this is not, in at least my view, the first day of class, this is just returning from a summer break, and now we are ready to jump in. So I know that you have already anticipated today saying, what are we doing now? For those of you coming out of Physics 121, you're done with your mechanics. That could be a good thing or a bad thing, depending if you like the mechanics or if you're good at the mechanics or you're going into mechanical engineering or whatever. But as to be very obvious and very clear, these 3 semesters of physics, we study a lot of different topics. Some of you, again, have only done 121 and you've only seen mechanics and mechanics of solids and mechanics of fluids, and now we're going to get into a different topic. And so we start right away with electricity, and we spend about 4 or 5 weeks with electricity and 4 and 5 weeks on magnetism, and then 4 to 5 weeks on the mixture of the two together at the same time. And that's where it really gets fun, interesting, and challenging. All right. And so that's kind of the layout of the semester. Others of you are coming out of Physics 123, and of course you've had other topics there. That's the class for that. What did we do in that class? We did mechanical waves, then we did thermodynamics, then we did optics, and then we did some quantum mechanics and some relativity. And so we had a lot more different topics. But this course then is one main topic put together, electricity and magnetism. And so that's where we're headed. Now I'm just stalling here long enough to get the syllabus in front of you, hopefully. And so it looks like it's about halfway back. Oops, that's not the syllabus. This is the syllabus. But I'd like to take a quick look at the syllabus. And it's a quick look in 2 parts. Number 1, because with other than a few exceptions, all of you have had me for 1 or 2 or 3 or 4 or 5 semesters, as some cases may be here, but many of you have had me for in the area of 2 to 3, because you probably had me for 102, and then you had me for 121, and now you're here, or you've also had me for 123. So this is our 3rd or 4th semester together, and the layout of my class is exactly the same, the syllabus is exactly the same, and so I will highlight that. And for those of you who are new, then please look it over, and you will see you will see the information written here. I don't see my Chrome. Maybe I'll just do Internet Explorer here. See what the default is. All right, well that's close enough. And just as well, I'll start here at the City College. Let's see, I'll go to college departments. I'll go to academic departments. I'll click on P for physics. I'll click on physics, and then finally getting to what I want to show, if you haven't seen this before, is where we control the web page. And so I will click there, which then lists all the faculty that teach for us. And there is me. And then finally, get to my web page, scroll down a little bit. These are the classes I teach, and this is where I want to begin here. So here's the syllabus. Here is what I want to take the first, say, 20 minutes or so before we kind of just jump right in. And like I said, it's not really an introduction today because this isn't an introduction. We're in the middle of the book. We are going to start in chapter 23. And maybe a quick warning here, this is not like chapter 1 of the book back in Physics 121. I met those guys yesterday. You might remember that first day. And we had to convert centimeters to meters. Ooh, that was hard. Or the real tough one, miles to meters. There was a tough lecture, right? No, we're in the middle of the book. We're in chapter 23, and it's one of the harder chapters of the entire book here. So, little forewarning here, this is a rude awakening, if you will, if you haven't been focusing on doing math or studying. It's a good thing you're back and refreshed, because this is a fun and pretty advanced chapter. Well, more on that in just a second, but I did want to skim through this. Obviously, there's my name, my office and lab and work area. There's my phone number there. There's my email address. Here is a quick description of what the class is, which is essentially what I just said. Here's where we will get into all of our electricity and magnetic stuff. And in fact, it even lists it. First we'll do electrostatics today, and then DC circuits, and on to magnetism, then electromagnetism, alternating currents, electromagnetic radiation, and finally we'll finish with electromagnetic waves. You're obviously enrolled in one of the labs. And then here's Don's class, the Physics 199. Oh, and I should add one thing new here. Oh, yes, I almost forgot about this. Is that in the past, anyways, we just called it Physics 199, and students took the Physics 199. You guys know what I'm talking about, right? The Don Help class? Okay. And I encourage everyone to, of course, sign up for it again. Obviously, Don is great, and you get great help on Friday, and he does those great reviews for you. And has this happened to anybody? They're not letting some classes, or a lot of classes, sign up twice. So if you already took this class for Physics 121, let's say, the computer's blocking you from taking it again. And so that's why, if you look on the course offerings, you'll see a very new class called Physics 122W. Okay? And so sign up for that. So I have not changed it on my syllabus, and it's just something that is totally new this semester, but it really is the same thing. It is, you're going to go and to the lab, visit with Don on Friday afternoon. And like I said, the computer is blocking you now, and so I have brought out at least some add codes. It may not be enough, but at the end of the class, I would encourage those of you who aren't signed up with the help session with Don to grab one of these add codes. So you won't be signing up for Physics 199. You'll be signing up for 122W. And those of you moving forward next semester into 123, be on the lookout in the catalog for 123W. So it's all going to change to where you sign up for 121, and then the help class is 121W. And then when you sign up for 122, the help class is 122W, W for workshop, and then 123 and 123 workshop. So the 199 will be phased out. So that's a new requirement of community colleges, is to not allow students to repeat classes if they got a passing grade, which in itself is a whole argument, but when it comes to the 199 class, that's a shame, but that's okay. We'll just have different workshops for the different classes. And so that's our answer to it. All right, well, continuing on, I think you know the textbook. I told you guys when you got started, if it was last semester or whatever semester, you had Physics 121 with me. But here's the survey book. You can grab whatever edition you want, the 7th, the 8th, the 9th. But I said I wouldn't change it on you so that whatever one you purchased, you don't have to buy another one. And so the 7th is getting a little bit on the old side, but it is a great book. And more importantly, it is a cheap book because it is not the latest edition. So it's like buying a used car versus a new car, but it's still a good, reliable car, and it can save a lot of money here. So that's the idea there. So any of you who are new and you saw that, whatever edition you got is fine, but the 7th edition is the one that I will be carrying with me and encourage you to get. In fact, those of you who might be new, let me also point out that I'm carrying the lighter version because I'm old and weak, but the book you want to buy is a little bit thicker than this. It says with modern physics, and that part of the book we need for the 3rd semester, the Physics 123. So make sure your book says that. Now, you won't need those last chapters for this semester. That's why I'm going to carry this lighter one. But those of you who carry the heavy one get an extra unit of PE too this semester. Did I see a question? Yeah, Danny.
So if you've been here for Physics 123 or Physics 121 and you already have the book already, you don't need to buy it.
Exactly, exactly. Do not buy a new book. And for those of you who might have, and you guys already know this, an edition other than the 7th edition, the problem packet right there has the problems from the 7th edition. So get yourself one of those. The grading procedure, same as before, 3 exams, labs, homework, final exam. Additional help is on the next page, so if you find yourself struggling, one of the first things I'm going to ask if you talk to me is, are you really taking advantage of Don and all the great work and all the help that he gives you? And so again, it says Physics 199, but whether you sign up for 199 or 122W, it's the same idea. It's that workshop class. And so that's the best place to go. It's, obviously Don is extremely helpful, and helpful not just during Fridays, but obviously during the week as you guys stop by and see him. Oh, we do have a tutoring service, and so I will pass out some hours for that. We have 12 hours. They're almost solidified, if you will, but sometime during this first week, that's what I do, is I figure out what tutors, what hours I can get them and get them assigned, and I will pass that out the next Tuesday, and you will have the tutoring hours. So you might want to swing into there. But I would encourage you, really for the same reason that the 199 is really nice, because it has a chance for you to get together with people that are in your class, and what I call forming study communities, and you get together and you talk and you ask questions, and you learn a lot as somebody asks you a question and you try to explain it, or if you ask somebody a question, and just the talking about it is what's really, really nice about that Friday afternoon workshop. Likewise, the tutoring center is that way. Now, the amount of tutoring hours we have in a week is kind of small. It's only 12. But that aside, it's a great place to get some work done. And so if you poke in there, and I got to admit, in the last few years, it's been getting kind of crowded in there. It used to be nice and quiet in there. There is the study rooms in the back, but if you can find somebody and be working with them and studying with them, it helps a lot. Another thing is, and you guys are, I think already know this too, but this class also, I guess it was last year, we videotaped them, and so they're on our YouTube channel, and so all the lectures from last fall are there, and we're going to shoot it again here. So we got David in the back there running the camera, and we're going to shoot it again. And I guess I got to figure out what we do. Do we put it side by side as a parallel lecture and you can look at either one, or do we look at which one and see which one came out both and delete. I don't know. So that we have yet to figure out. I guess I'm kind of thinking side by side. And well, this was fall of 2012 and this was fall of 2013, whichever one you want here. But anyways, there are a lot of like I said, all the videos are doing, and MIT does the same thing, and so they've got their courses on there, and I think that's an excellent place to see. So I recommend those books. If you're into outline series, I particularly like the Shams outline series. I'll throw that back out there, and I'll even go beyond this class. I mean, if you obviously are struggling with this class, a great place after you've done these other things, and after of course you've just done the reading and the homework and come to class and tried it on your own, outline series I think are fantastic. And so if you have not been acquainted with outline series, they're really great. Sham puts out a great one. It's called College Physics. You can pick it up, and he just kind of summarizes really quick what is that particular topic. And so you can get to the electricity, and today we're going to do electrostatics, and you can just read about electrostatics, and it's really an outline. It's just one page, so in no way would it replace your textbook. It doesn't have enough detail for that, but what it does is summarize the book, and it does that really well. And so I would encourage you, not just in this class, but if you find yourself struggling in Math 200, which is what, multivariable. There's one on multivariables. You find yourself struggling in chemistry, there's a great one on chemistry. If you find yourself struggling with linear algebra, there's a great one on linear algebra. Oh, and the one on differential equations is phenomenal. So if you'll view in 220, it's just awesome. So anyways, but I was introduced to it about when I was about your age, back a century or two ago, where they and I just constantly picked them up. So I've got some old ones from chemistry and physics and advanced classes. They're just really good. Anyways, there is a few others out here. I can let you read about them, but I'm going to move forward.
What are those videos about? Like you find them on
which videos?
The videos about like something you might have on the differential equations or linear algebra.
Oh, now what I was just saying, Danny, was that this, where is it? I'm talking about a book. It's an outline series. They're short, they're concise, they're really good. And so after you've done that the first time, the outline series are an excellent supplement to that. Now going one step back, the videos, at least for physics, I have done for us. MIT has done them also for physics, but also for differential equations. So if that's what you're asking, I can't really comment on how good they are in the differential equations at the open, what do they call that? The open courseware. But given that I think the other ones they've done are really good, I would assume that their math ones are pretty good too. In fact, I have even seen students in the past watching the MIT differential equation ones when they're supposed to be doing my lab, yeah. So, but you guys wouldn't do that. Of course not.
Does MIT use the same book as us? Physics?
No, I don't believe so. Yeah, so they're not using the same book, but these are lectures anyways, and so the professor's lecturing with, with not really in reference to any book. And I don't think they have the same approach that I do, where they, you know how I do it is I talk about the material and then say, let's do some examples from the book. And I don't think they do that. They don't do examples from the book. They just, hey, let's lecture on the material, and then you go do the problems. It's MIT. Yeah. They don't need any examples, right? Scrolling down, then this is your homework assignment. And so this is the packet that you have in front of you. I think the packet has just the first 4 chapters, because here's where we're headed here at the beginning here. 1, 2, 3, 4, and then we'll have our test. So chapters 23 through 26 is our first assignment. And of course the last page here in the syllabus is probably the most important part here of the syllabus, is where we are, where are we headed, what is on the test, when are the tests here. And so kind of looking at this, you'll see this first week right here, August 26th through the 30th, we're going to do chapter 23, and the lab we do is static electricity. And so tomorrow, 1/3 of you will do the, well, tomorrow morning, 1/3 of you will do the lab. mid-morning, another third of you will do the lab, and Thursday afternoon, the other third of you will do the lab, and this will be your lab equipment. And so I'm hopefully going to show you the beginning parts here of chapter 23 and what we call electrostatic, and then of course what I do now you are going to repeat in the lab tomorrow, so you can get your hands dirty and hopefully make sense out of the stuff I'm doing. So I will explain it the first time, and then you will hopefully read it a second time, and then you will do the lab on it a third time, and then you will do a homework on it the fourth time, and by that time you're experts at it, so you will take a test on it and score 100% on it when you get to the test. But that's our goal here then for this week. And if you scroll down a couple of weeks or look down here, you will see next week we do chapter 24, next week we do chapter 25, the week after that we do 26, which kind of flows into that Tuesday, and then in week 5 we have a test then on our first 4 chapters, 23, 24, 25, and 26. And so that's our goal before we get into the next little part, which is electrical circuits and electrical current. All right, well, like I said, that's kind of the introduction, if you will, the beginning. I will pause and say, any questions? Am I missing anything? Are we ready to jump in? Oh, and maybe I should say, particularly for those of you who might be new, don't forget to get a lab manual. I kind of skimmed over that there and what it says textbook, but you need A, the textbook, and then B, you need the lab manual. And so this you can only get at the bookstore there. It's not real expensive, but make sure you pick it up before your lab tomorrow or Thursday.
I think the labs weren't 3 hours last semester. Are they going to be any different this?
It's kind of the same basic layout. The speed of the lab goes really in a combination of you and your partners and how fast you want to go. It's designed so, and I think this is what you're getting at, it's designed that the longest lab, because some labs are longer than others, and the slowest group of the longest lab will get it done in the 3 hours, which definitely means the majority of the time you'll be done before 3 hours. Yes, yes, yes. And maybe every time you're done before the 3 hours. How much kind of really depends on how much preparation you've done ahead of time is what I've noticed. People who come in and they don't really know the material struggle a lot longer in the lab, and it takes a lot longer. Which is okay, which is good, because that's why they're struggling. They're learning along the way. And those who have already have the material or understand the material kind of go through the lab very quickly at that point. Yeah. All right, well, if there are no other questions, shall we begin? Chapter 23. Now, I'm going to make a guess. Oh, yeah, question.
So you said the grading is the exact same, no plus minuses now?
I'm glad you bring that up. Yes, the college has moved to a plus-minus system. Or actually, I should say they've moved to an optional plus-minus system. And there's been a lot of talk about it. And here, I guess here's what I'm going to say formally is, no, I'm not adopting it yet. I'm a little concerned about that A minus. Those of you who get the 90%, you know, you just make that A and then you don't get a 4. Oh, you get 3.7 because you get the A minus. So I'm not going to do that. Long term, I'm going to think more about this, but as the semester goes along, there's just too many tough issues with it. So when they told us you can do whichever way you want, I go, okay, I'm going to stick to what I've been doing. All right, so that nobody gets lower than they did before. Yeah, yeah. I will probably, with that said, though, do the B plus so that there's going to be a little bit help. So if nobody has a complaint with that, since I didn't put it on my syllabus, I'm not really, you know, not supposed to do. But I think the B plus will be okay in the sense that everybody will get a little bit better than a B if you're that 89, and I'll do the B plus. But so I want to say formally, no, I'm not doing the plus minus system. But if a B plus shows up and you're not complaining, then great. And if you want to complain about the B+, I'll have to put it back to a B, because that's what I put on the syllabus. All right. All right, so as I said, I am sure all of you read chapter 23 last night, right? All right, I'm not asking for an answer, but I do want to repeat that something I've said in the past is a really nice way that will help you learning is the following. Start with, can we squeeze you guys in? I think there's some stools on the side there. I should have said that to somebody if you want to swing over there and grab a stool, and you guys in the back there, if you wanted to grab a stool, or maybe I didn't even grab. I think there's 4 out there. I grabbed thinking that there would be some standing here. And then, of course, remember our lab has some. And we are full. We need to get a bigger room, and working on that. It didn't work out this semester, but next fall, which isn't going to help you guys this fall, but we're gonna have a bigger room or something different, as we have way too many bodies for us, and we could do that now. All right, so what was I saying? What I was saying here is a good learning strategy, and I'll repeat it again. Read it like a novel before you come to class. And what I mean by the read it like a novel is, since you are reading it through the first time, and this is very technical material, you may not catch everything, or it may not make complete sense. Don't let that bother you. Go ahead and just keep reading it. Because this, believe it or not, actually can be very helpful. People think, oh, I didn't completely understand it. You're right. You didn't completely understand it when you read it last night. That's not the real point. The real point is it has really primed the pump, if you will. It has set the stage. If you like doing jigsaw puzzles, you may think you've done nothing but, oh, I got the box, I opened the box, I poured out the pieces, I turned over the pieces. Okay, now I'm ready to get started. But all of that prep work really gets you into the position of ready to learn. And so just reading it, just seeing the pictures, the diagrams, the vocabulary, all of those can be really beneficial, where you may feel like I haven't learned anything. Boy, it's amazing then when you come in for the lecture how your learning really starts to take place in a much more dynamic way than if you hadn't done the reading ahead of time. And so I have always encouraged that. I will say it again, and some of you, I know that has worked for you, and I know that you even commented before you saw me this morning, hey, I read chapter 23. So good for you, because that's what I want to jump in. I want to look at chapter 23. It's after you hear the lecture on chapter 23, which is today. I would encourage you then to go home, and then that's when you read it like a textbook. That's the part where you read section 1 and you don't go to section 2 until you understand section 1. And you say, okay, I know section 2. To fully understand section 2, it needs a full understanding of section 1, and so you go back and maybe you read and reread section 1, and then you read and reread section 2, and read and reread section 3, so forth and so on. And even then, as you are probably aware well of, you end up pausing at when you sit down to do the homework and go, I better go back and look at that. I remember reading that in section 3, and here's a problem on it, and I thought I really understood it, and then I tried to do it and kind of got bogged down a little bit. So let's get started. Here is chapter 23. Chapter 23 is trying to introduce you to the electrical field. And so for those of you who got a chance to look, that's what the title says, electric field. What are electric fields? I'm not sure we'll get that far today, but definitely on Thursday. That's what this week is about. What is the electric field? And before we even get that far, let me just pause. Maybe I'll even jump over to here and say, let's look at the structure of an atom. What does an atom look like? And so going back to your Physics 102 or whatever physics you took before you started this sequence somewhere in high school, you probably said, let's look at, say, helium. Helium's a good one, I think, to teach from because it's not the simplest one, hydrogen is, but it's the next simplest one, and it's complex enough to show all the inner workings. If you could take a photograph of this atom, what would it look like?
You see almost nothing because these atoms are linear on so fast you barely see them. So that energy space is very fast.
Okay, so you said my point. There are these things called electrons. There's this thing called a nucleus. Inside the nucleus, there are two other things called protons and neutrons. And that's what I want to review here for a moment. So this inside piece, this nucleus, has two objects, protons and neutrons. The outside piece has electrons. And so we've got electrons on the outside and protons on the inside. Why I point that out is the following. Let's look at this periodic table. Let's find helium. Now, of course, helium is the first row on the far right there. It's the big blue number 2 there. And as I look at there, or green number 2, it's got a green number 2 and it's got a black number 4. So help me out again. What does the big green number 2 mean? The number of protons in the nucleus. So the whole reason I colored these in is because I was trying in my little diagram here to show you that this atom has some protons in it. How many? 2. It also then has something else in the nucleus. Neutrons. How many? 2. Now, why 2? How'd I know there was a 2? Yeah, so the 4, remember, is telling me the total number in the nucleus, what we called its nucleon number. So the total number is 4. And then 2 of those are protons. So to get the number of neutrons, I have to subtract. So the number of neutrons isn't explicitly listed in the table, but I can figure it out with a little bit of math, a little subtraction here. So 4 minus 2 gives me 2. So I've got 2 neutrons, 2 protons. So that's what's in the nucleus. All right, fine. And then on the outside are these electrons. And as we will quickly see, which is the topic of this semester, is there will be 2 electrons, and I heard somebody say at least on average it may lose 1 or gain 1, but in general it wants to have 2 because our focus is this. These electrons and these protons carry with them a thing called charge, electrical charge. And so we have 2 different charged objects. Electrons containing what we will refer to as the negative charge, and these protons, which we will refer to as a positive charge. Now, I probably shouldn't spend too much time here because, first of all, your author does not look at the structure of the atom in any way here at the beginning of the chapter. But it is to remind you here that we are going to be looking at charges. And the charges come from with the atom itself. So our beginning steps, in the lab you will do tomorrow, and what I want to show you here today is something like this. Here are some experiments that you are going to do. They're very similar to what Benjamin Franklin did as he came up with this idea that some things are positive and some things are negative. The materials I will use are not the same materials that Franklin used. We will use more modern materials. But this one right here is vinyl. And so what Franklin realized and what you need to realize in the lab and what I want to show you today here is if I were to take 2 materials, which in this case, I've got a piece of vinyl and a piece of paper. If I put them together and rub, What's touching? As this piece of vinyl hits this piece of paper and I scrape and I rub, what touches? Yeah, and here's the idea of why I wanted to start with the structure of the matter. If I were to bring two materials together, which again in my diagram it's kind of showing helium coming together, but given what I have, it's probably carbon coming together. But when two atoms come together and they bump and they rub and you scrape them, what touches? Yeah, right there. It is the electrons. Maybe some numbers are worth being in order. The size of an atom is about 10 to the minus 10th meters. The size of a nucleus is 100,000 times smaller. That's about the same dimensions as, you know, our athletic field, our football field down here, soccer field. If that field was a nucleus, then where's the electron? Well, 1,000 times further. So we're talking about New York City here, right? That's all empty space between our field and New York. And so that's what we have. So there's a lot of room between these two. And so as I scrape and I bump and I rub, it's the electrons only that interact. It's not the nucleus that gets close to another nucleus. It's not even the nucleus that gets close to another electron. It's that the two electrons get close together. Here's why I say that. Here's the mental picture I want you to have. I'm going to put a piece of, I'll call it vinyl here on the board and say, okay, this represents my piece of vinyl. And that will be my focus. I won't bother to draw the paper on here, but what you saw me do, and I lost which side it was. Bummer. Well, I'm going to do it again. And so on one side, what I did was pinch with my fingers really hard and take the acetate and rub real hard. And what I'm trying to do here is knock off a few electrons. And when they bump, as this picture is trying to show, these will come free. Now, as they come free, they're going to go back to the material. But one material will be a little bit stronger and grab the electrons more than the other. And this is the whole point of me taking two different types of material. So as I rub this, I am kicking electrons and freeing them, and then they grab back to whatever material grabs them the most. We call this, which one is the most electronegative? Now, let's not get into the chemistry of why one is more electronegative than the other. That's a little too early for us to do that. But my point is that if vinyl is the more electronegative one, which it is, what then is happening on a molecular level, if you could see this with your eyes? I bump it, I free them, the electrons all get grabbed back to this one. And so what's different now that I rubbed it compared to before I rubbed it? Exactly. And what I want you to see, mentally of course, because we're too small to see physically, is that before I got started, there was an equal number of positives and negatives on this piece of vinyl. And so this piece of vinyl, I'm going to refer to it as neutral. Not zero charge, although you might call it zero net charge. Please note that there is positives and negatives on that piece of vinyl. Again, that's why I started the chapter here saying, never forget what an atom looks like. An atom, although we may say it is neutral, does not mean it has no charge. What it means, it has an equal number of positives and negatives. And so that's where I got started. I got started with an equal number of positives and negatives. And then I came along with a piece of paper and I was rubbing it, and I was rubbing it and bumping, a bunch of electrons broke off, both of the vinyl and of the paper. But as they got attracted back, they went to the vinyl. So maybe I will represent that with some extra negatives on my piece of vinyl. And so what I'm going to say about this piece of vinyl right now is it is negative. Now, again, want to make that real clear. I'm calling it negative. Does that mean it doesn't have any positives? No. What do I mean when I call something negative? More negatives than positives. Okay? And you're going to see the other way around. If I call something positive, does it have negatives? And the answer is going to be yes. But I call it positive because it has more positives than negatives. So more on that in just a second. Yeah.
So these electrons, do they go straight into the orbital of the atom, or do they just hover on top of it?
On top.
Okay, because if it was going into the atom, that would technically change the chemical properties of that atom.
Oh yeah, yeah. So they're hanging around on top, and again, a little premature to kind of answer that. That's actually a very good question for our next chapter. We start asking where are these electrons, and then the answer is going to vary depending on whether they are insulators or conductors. But for this part, I'm just going to rub. And that's the first mental picture I want you to have as we get started today. That take any two materials, you rub them. Because of the structure of the atom, the electrons free off. Because one is always going to be stronger than the other, they're going to go to one material versus the other. Without getting into material science or chemistry, we won't know which one, so I'm going to tell you. It goes to the vinyl. And so I would start my discussion here and say, that piece right here is negative. Vinyl is negative. And if I were to ask you where the electrons came from, you would say?
The other thing.
Here. And so I want you to notice, I didn't create the electrons. I didn't rub them and make extra negative charges, did I? Where did it come from? The piece of paper. Mm-hmm.
So if the vinyl picks up a negative charge, does that make that piece of paper picking up a positive charge?
Excellent. There's my next question. What about this guy? What would this look like on a microscopic level? And I said I wasn't going to draw the paper. I lied, I guess. I am going to draw the paper. Here is your question. Here is the paper. And again, before I started this little experiment, there was positives and negatives. And we may have called the piece of paper neutral, but again, we didn't mean it had no charge. What we meant is it had an equal number of positives and negatives. And so when I was rubbing them, again, bouncing the electrons off of each other so that some of them went over to the vinyl, as you pointed out, what about the paper now? Well, the paper now is missing a few electrons. And so I will call the paper and maybe even represent the paper with a positive charge. And so yes, the paper is positive. And again, I hope you see this mental picture, because the whole reason I want to spend at least an hour, maybe an hour and a half of just giving you this mental picture, because I'm sure you realize that the real work is going to become in calculations and all our wonderful calculus here. But before we can even get into the calculus, you really need to understand this conceptually. Probably more than any other topic we've done here is a good mental picture of this, and a good understanding will stop you from doing some crazy calculations that make absolutely no sense. And one of those you see right away. One of those you hopefully see, there is never an increase of electrons here. What happened is a transfer of electrons. They left the paper and went over to the vinyl. And so as we think about what happens in the lab, and as we think about the problems we do, and particularly when we get to our electronics and our capacitors, we need to remember that. There's not just all of a sudden more electrons that show up. They came from somewhere. And so when we call something negative like this, what we mean is electrons came from somewhere else. They came from, in this case, the paper over to the vinyl, and this piece of vinyl has more negatives than positive, and that's why we call it negative. And yet this piece of vinyl does have positives on it. And that is really, really setting the stage for the next couple of chapters, that you see that. And likewise over here for this piece of paper. This piece of paper then we call positive, and please remember how it got positive. We didn't create any positive. In fact, more than that, we didn't even move any positives. How did it become positive? Lost negatives. Something is positive because it has more positives than negatives, but that doesn't mean you put positives on it, because it could mean you take negatives off, and that's what happened in this case.
Wait, does this mean you're tearing off electrons off the surface of the atom?
Yes.
So does it mean it would not change the chemical properties of the paper as well, or just so minute? It's just
Minute. Yeah, so no.
That's not noticeable.
Yeah, but yeah.
So what happened when you rub two of the same two?
Oh, yeah, rubbing two of the material doesn't give you much result, because first when you rub them, you scrape them off. Then when they get sucked back, they get sucked back equally, and you don't get any. So this experiment would not work well if I rubbed paper with paper. Well, that's hard too. But besides the mechanics of rubbing paper against paper, I'm not going to get any separation of charge. So I happen to pick one material, modern material, that sucks electrons up like crazy. That's why I like to do the vinyl. Franklin used a rubber rod, which isn't bad, but it doesn't work nearly as nice as vinyl. So what I want to show you...
Metal likes to lose its electrons?
Let me just shortly say no. Yeah, no, no.
How do you determine which material earns the electrons and which one uses?
Well, yeah, again, okay, I want to emphasize here. I do not expect you to know whether the electrons are going to go to the vinyl or to the paper. That is not what is required of this class. That is a good question, and is a question that is a question in a chemistry class. It's a good question in a material science class. But for us today, I'm just going to tell you vinyl is more electronegative than paper. And it happens to do with the way the structure of the molecules are connected, and I'm going to leave it at that. Okay? So it's not a complete answer, but it is, you know, we got to take one step at a time.
How did they initially distinguish between positive and negative?
Well, they didn't. Franklin did this. Franklin said, I'm not sure which way the electrons are going, but I'm just going to call this negative. He didn't even know there were electrons. He just said, whatever I'm doing now, I'm not real sure what it is, but I'm going to call that negative. And so it wasn't until later that science learned this more complicated idea that there are these electrons, there are these protons, there is a nucleus, and the electrons are leaving one. So he just called it negative. And so we stuck to it. And there's good and bad about that, as you'll see as we go through the semester. Sometimes we'll be happy that he called this negative. Other times we'll be sad that he called this negative and not positive. Yeah.
So if you arbitrarily called it positive, it would have had positrons around the atom instead of...
Yeah. So at that point, it's just vernacular, it's vocabulary. Which one you want to call positive? But Franklin was smart enough to realize that of all these ones I'm going to show you today, and then what you're going to do in the lab, there's only two. There's only a positive and a negative, and that's the real beauty of hopefully what you'll see here in this hour and a half. Okay, because Franklin again knew this much, or at least reasoned out this much, that although I may not be sure what's going on when I rub it, whatever went on with this one most likely is happening again when I rub this one. So he took the same material, and as I said, in his case it was 2 pieces of rubber. In my case it's 2 pieces of acetate, and he rubs them. And he says, so whatever happened here, which you guys know far more than Franklin does now, and there you go, you're smarter than Ben Franklin. You're even smarter than Isaac Newton. He didn't even know there were electrons. He didn't even know there was Calc 2. He got Calc 1, but you know, Calc 2. So keep that in mind. All right. So back to the physics here. But what he realized is that what was ever going on, and then now you guys know that that's negative, these are negative. What happens when I bring 2 negatives near each other? Is there any interaction here? Yeah, what kind of interaction? Yeah, I would say there is repulsion here, right? And so what we are hopefully seeing here is one of the first discoveries by Franklin, that when you bring two negatives together, they interact, they repel. And so sure enough, two negatives repel. Now let me switch up the material a little bit. I'll put this vinyl over here. And let me try a different material. This is acetate. Now, as long as we're bringing up some history, Franklin did not have acetate, but he had glass. Acetate works much better, so I'm going to use the acetate here. But let's do the same type of experiment. Let me take a piece of acetate. And again, starting with this piece of acetate, which will have an equal number of positives and negatives, so we are going to say that the acetate starts off neutral. And I will take another piece of paper over here that I haven't messed with yet and say, okay, here's a piece of paper that's neutral. It's got an equal number of positives and negatives. I won't draw it on the board unless somebody asks me a question again, and I'll have to draw it on the board here. But for the most part, my focus is going to be on the acetate. But here's what I'm going to do. I'm going to take this piece of paper. I am going to put the piece of acetate between the paper, and I'm going to rub, rub, rub. Now, I hope by this point you have that same mental thought in your mind. What am I doing when I'm rubbing here? What's touching? Yeah, the electrons. And so they bump, they rub, they scrape off. Once they scrape off, though, they want to go back to the material. What material do they go to? Well, the one that's more electronegative. Now, I wouldn't expect you to know this, so I'm going to tell you. Paper now is more electronegative than acetate. That's why I picked the acetate. It's exactly the opposite of the vinyl. So this one's acetate. Can you guys see a slight difference in color? This one's kind of blue.
They're both.
And that's, yeah, but okay, fair enough. Does that look the same? Does that look different? Okay, yeah. So I'll try to say which one I have because I know it's hard to see. But this is the vinyl. It's got a little blue tint to it. But the acetate's clear. Uh-oh. What side was I rubbing? This side?
Yeah.
All right. So I don't know. I'm going to keep rubbing it because I want to get enough that you can actually see the results. But most of you are guessing it already. That if I rub this and the paper is more electronegative, what's going to happen to the acetate? Yeah, and so as I rub the acetate, I am scraping electrons off that end up on the paper. So the paper is now negative. The acetate is now positive. It is lacking electrons. If I take another piece, I'm going to keep my eye on that one, of acetate, and do the same thing, then again, Franklin didn't really know all the details of what were happening, but he did realize that when I rub these together, or when I do the same thing here, whatever this one became, which I'm telling you now is going to be positive, that this one would become positive. And then he brings them together to see, is there any interaction? Anything happening now? What do you notice about these two positives? Yeah, they repel. Well, if you let me draw a picture here, this is what I am trying to say, is the electrons are missing, so I will just put some positives around it to say, hey, I have a piece of acetate that is now positive, and the other one was positive. And you hopefully noticed a pattern here that when I brought two objects that were each negative, they repelled each other. And now I am bringing two objects that are both positive. They repel. Both cases repel. There is something slightly different about them. One case they're both negative, another case they're both positive, but we like to say these are like charges, so we can put them in the same category. And so like charges repel. And so the lesson here, well, it has many-fold, particularly the fact that we didn't create any electrons, we transferred them, one becomes positive, one becomes negative, and what do we mean by positive and negative? And when something is negative, that just means there's more negative than positives, but there are positives. But the final conclusion in all of this is two objects that are negative or two objects that are positive, as long as they have the same charge, as long as they have like charge, they repel. And I'm sure you saw that in 102. All right, now question, yeah.
So if they were to sit for a while, they start to lose their charge and become more neutral?
Yeah. Now,
where do those electrons come from, like the air?
Oh, yeah. Now, if I leave it sit here for a while, like this one's, well, like this one here is negative, this one here is positive. I haven't shown you that positives and negatives attract yet, but that's why when I rub them and they pull off and go back, that's why they go back. That's why this is going to go over to there. I'm going to show you that in just a second here. But in this case, something like this would probably happen. Here is why the water in the air is a crucial factor. You'll probably notice on this experiment, I put the here, trying to keep the water away. Fortunately, today it's not too much water in the air. We got a lot of humidity inland, but we don't have any fog. So I think today's going to work great. I'm hoping tomorrow morning we're not foggy, because I got to admit, one of the challenges of teaching this topic on the Southern California coast is that there's a good chance tomorrow you guys come into lab at 8 o'clock and it's foggy, but it's not supposed to be tomorrow. So we hit the week just right. Nice, beautiful, sunny, no foggy weather. Although it's a trade-off, because if it was foggy and cold, you guys would come to class. Now with it sunny, you might be out surfing. So
So obviously there's an upper capacity of how much static electricity, free electrons you can have, because as one side starts storing up too much electrons, it starts becoming the other side starts becoming more and more negative, and therefore this can't. The more you rub it, the more you rub it, infinity, it's just going to stay the same level of charge.
Yes, exactly. Good. And I'm going to get to that, but let me then show you the other half of this, because this is what you're coming up with. I have shown you the case. Oh, I don't think I finished mentioning the whole water process, but basically you take a water molecule here. The oxygen really loves electrons. And for those of you who have chemistry know that water gets very polar, and most of the electrons get sucked over towards the oxygen, meaning it is far away from the hydrogen. Now, the whole molecule is neutral, equal number of positives and negatives, but it is what we call polarized. And again, I will show you that in a few moments too. But what will end up happening is one of these negatives will hitch a ride on the back side of this. Once it grabs onto here, then this molecule is negative. You've got a negative molecule floating around with positives nearby. This thing's going to migrate over to here and deposit that negative, and so the electrons will float around on water molecules. And there's other mechanisms too, but that's a big one of water. And so that's why I'm trying to keep things dry up here. The water just kind of destroys this. So when I come back to this, I'm going to re-rub them because they're not as charged as they once were 5 minutes ago. Yeah. All right, so back to this other picture here. This other picture is, then what would happen if I took a positive object and brought it near a negative object? Or the other way around, what if a negative was first and then a positive? And on that one, as you might expect, that shouldn't matter which order that one is, but let's look at that one. And so I'll start with this first one, positive. I will ask you, since you'll need to remember this for the lab tomorrow, which one becomes positive when I rub it? Is it the vinyl or is it the acetate? Yeah, it's the acetate. So again, remember that the acetate, its electronegativity is very, very low. And the paper is going to get. And so one of these sides I rubbed. I need to mark it. But I'm just going to rub it again. And so I'm going to rub this side. And hopefully that scraping and grinding will take electrons off of the acetate. and I will have a positive object. If I jump back over to here and get my vinyl, see it's kind of blue color that I was rubbing before, then this should scrape and bump the paper and take electrons and put them on the vinyl, so this should be negative. And so what happens when a negative is near a positive? And I'm hoping you can see I get an attraction. And the reverse would also be true, that if I started with the one hanging, which is the vinyl, and I rub it, and it is negative, and I take the acetate, which is now positive, and bring them together, that too will result in a little bit of attraction. And so, finishing up my diagram here, I would put 2 arrows pointing in or 2 arrows pointing in and say that these attract. And these are what we will call unlike charges. And so obviously we haven't gotten into numbers, any calculus yet. Don't worry, that's coming in case you felt cheated, like you really wanted to do a lot of hard problems. You certainly will this weekend. But the first step is just to realize the conceptual picture of what is going on a molecular level. You will need that. It'll carry you a long way, keeping that mental picture, what is happening to these electrons, and just knowing then that unlike charges attract and like charges repel.
So how come the acid doesn't like explode on itself? So how come that positive charge doesn't attract the negative?
Oh, I'll give you a second, I'll answer that, but I also then wanted to point out here then that it's this opposite one that I kind of indirectly had been using before I got a chance to talk about it, when I said I rubbed these and freed up the electrons, and the electrons were pulled back. Why were they pulled back? Well, they were pulled back because I had taken the electrons off of the material and leaving behind the positive. So they're going to want to go back. It's also why Danny was then pointing out here that if I rub this, there's only a certain limit that I can charge this up to. Because as I start scraping more and more, let's see, this is the acetate. So as I am scraping more and more electrons off of the acetate, this object is becoming more and more positive, and at some point it's just too difficult for more to come off. As I try to scrape them, instead of coming onto the paper, this now becomes more electronegative and goes back. So I have a certain limit. I can only get it so much charge. Fortunately, there is enough charge that you can see the result. All right, now on to your question. What was it again?
Why doesn't the atom implode?
Oh, and then why doesn't the atom implode? There is something else going on, and I'm going to, I guess I'll answer it at 2 levels. The first level, everybody who's had 121 will understand here, that if I would say it wants to implode in the same way the Earth and the Sun want to come together and implode. And so if I have a positive and a negative, or if I have the Sun and the Earth, if they weren't moving, they would implode, right? The Earth would be. But fortunately for us on Earth, there is a movement. And so as the Earth gets pulled in, the force from the Sun doesn't have the Earth come and hit the Sun, but changes its direction as it goes around. So the same thing can be said about the electron. The electron does not actually hit the nucleus because it is in an orbit. It is going around. If it was stationary, it would. Although then that deserves a second level answer from our Physics 123, and how much do I answer on that? But this is getting into our quantum mechanics. The electron can't get that small. If you remember from our quantum mechanics in 123, I don't know if you remember that particle in the box, as it got smaller and smaller and smaller, that first energy level got higher and higher and higher. So if you actually and tried to put this electron into the nucleus, remember the nucleus is 100,000 times smaller than the atom. If you tried to force that electron into a box that is 100,000 times smaller, the energy would go up by 100,000 squared. That's 10 billion times more energy. Then it would have too much energy that the proton can't attract it. It's going too fast and it pops back out. So if that made sense, great. But hopefully the first level answer from our mechanics was better than my second answer. And so some of you, probably about half of you, have done the quantum mechanics back in May, although we did it kind of quick, so hopefully that somewhat helped. All right, well, I'll keep going, because as I said, this is one of the first things you do. Look, if that all made sense to you, let me try something different. Let me come over here and grab a hanging object. Now, this hanging object happens to be what we call an aluminum pith ball. It's aluminum because, as I think you can see, at least I hope, I know it's a big lecture, but can you guys see this hanging aluminum object? It's kind of shiny and silvery in color. That's because it's got aluminum on the outside. Now, it's not solid aluminum, because then it would be too heavy for it to move around and for you to see. So underneath it, we have that pith material, or actually, this is probably cork, because we're kind of modern, but pith is that light wood that you see those African safari pith hats type thing. You know, they take the light wood and they put it on so it's airy and cool. Cork. Cork, okay. So we've got cork in the center just to give it volume and make it light. And then we've got aluminum painted on the outside. And the aluminum is going to become an important discussion here. It's going to be a conductor. But more on that in just a second. Let me just try something here. Now this piece of paper I've beat up pretty good, so maybe I'll jump to a fresh piece of paper as we continue on here. I'm going to go ahead and take a piece of paper and one of these materials. Let's see, this one is blue tinted, so this is the vinyl. Try something a little bit different. Does this make sense to you? I'm going to rub it. Rub it hard. Maybe extra rubbing, which, by the way, tomorrow in lab or Thursday in lab, make sure you rub your stuff really well. I mean, you should pinch it hard and you should feel it get really warm. Not to the point that you burn or cut yourself, but if you do that, that should be good enough, right? You want to get it really warm, especially in the morning hours, and especially if there's any fog rolling in the morning. But I'm going to just come along and touch the ball, pull back, rub it again, and bring it close. Do you notice anything? Do you see anything? Can you see it repelling away? And why? What have I done?
When you touch it, shouldn't it like attract, then like kind of like bounce off because the negative charge from there is transferred?
It did a little bit. I was hoping you wouldn't notice that till my next discussion. But yes, it did. There it goes again. Did you kind of see it real quick?
Yeah.
Yeah. Okay. And you are supposed to see that eventually, but give me 15 minutes and you'll do it in the lab. But at least at this point, do you see it repelling away? Why? What happened exactly? You guys see it. We were really talking about like charges here. If I were to draw a picture of this, it would look something along these lines. I will start with that little hanging cylinder object. And as you'll see, some of our equipment is a cylinder. The ones I have today are a cylinder. Some of them we have spheres. I personally like the spheres better, but I guess these were in the front and I grabbed them. But when you guys do the lab, some of you will have spheres, some of you have cylinders. That's not important to its shape. What is important, hopefully, is that you realize that I got started by rubbing the acetate. So what charge is the acetate? Negative. Very good. And so I had scraped electrons off of the paper onto the acetate. And then I came along and I touched the pith ball, the cork ball, the moment I touched it, what do you think happened? Right, and then so some of the electrons actually transferred. And so I didn't actually rub the pith ball in this case, so you might say this is something a little bit different, but I did touch it in the sense that when they touched here, the metal grabbed them, and I'm going to throw another word out here in a minute, conductor, meaning the electrons could flow or move throughout the material. And so where I touched it, these are now gone, and the negatives are now on that pith ball. And not a surprise, I even came back and I rubbed the acetate again to put more negatives back on there, because some of them got sucked off because they went on the pith ball. And then when I brought it back a second time, as you guys said, the pith ball is now negative because I made contact with it. And so I'm showing you that I could get that pith ball negative, not by rubbing it, by touching it to another negative object. And there's no new physics here. These two repel each other for the same reason we saw earlier, that when two negatives are brought together, they repel. And that's what you see. But you also saw a little bit about conductors and insulators. So let me add to this. Yeah.
Is it because the metal is more electronegative, or is it?
Well, again, I'll say yes to that, but it's the same question about metals. And at this point, I guess I want to talk about them as conductors.
So if it was positive and then you touched it, would the metal have gotten the positive?
Oh. Let me add something very important here. Have you noticed every experiment I've done, and every experiment I will do, what charges are moving around, the negatives or the positives? Right? Did the positives ever move? No. Right. So I forget now which way you said it, but your ending part was you said, would the positives move? No. You can make things positive, but the positives are not moving. The positives are part of the material itself. They are in the nucleus, at least in solids. I should phrase that with solids. You are never going to have positives move, because that is what we mean by a solid. The atoms are locked into place, and the atoms are where the positives are. So what moves around are the negatives. And of course, you can make them positive by taking negatives off, but you don't make it positive by putting positives on. Okay. Well, anyways, I'm going to again show you a bunch of examples. This is the point of this first hour of the lecture, or let's see, syllabus was about a half hour, so yeah, so we're still within our first hour. But this is the goal here, is to get you this conceptual picture, and that's the point of the lab, is to make you go through and rub these and play with them and watch them push and pull on each other and try to get a mental picture of what is going on, because we need that mental picture before we can do the next step, which is to calculate how much charge, and calculate the concentration of charge, and calculate the force between these ones. And that's going to be the second part of the chapter. And so we're building up to that, but this is what I would call the conceptual side first, before we apply our mathematics and get some numbers in here. And so sure enough, these do repel. Now, as I said, you also saw something interesting in here, which leads to these words conductors and insulator. What do I mean by the phrase conductor? What do I mean by the phrase insulator? Well, I didn't actually say this was an insulator, or for that matter a conductor. It's not, it's an insulator. But when I took this piece of vinyl and I was rubbing, and the electrons came off of the paper and got stuck here on the vinyl, if that electron that is stuck cannot move in the material, it's stuck there, that's called an insulator. So an insulator is simply pieces of plastic and rubber and a lot of other insulators. Air is an insulator. And so what you are seeing right now is the effect of this an insulator and the air an insulator. That electron is there and it's stuck there. Does that electron move down to here and move onto my hand and move onto my body? No. No, it can't move in the material. Now, a water molecule could come by and grab it and bump into it and pull it off. But it cannot move in the material itself. And so an insulator is one where what you saw was this. I put the electrons there and they stayed there. So when I came along and I touched it to the pit ball, the negative that was here was able to go over to here once I made contact. But when there was air between them, could that electron jump over to there? No, because air is a insulator, right? And so we're going to say anything where the electrons cannot move in are called insulators. Things where the electrons can move are called conductors. Now, of course, that brings up that whole question. Why is something an insulator, some is a conductor? And I'll stop there. Let's wait until we have material science. Let's wait until we have chemistry. But at least let's understand the properties of what we call an insulator versus a conductor. That's where we want to go. Yeah.
All liquids aren't conductors, are they?
No.
Then how does that work with liquids, with the electrons not being able to move?
Well, they would be hooked to that molecule, and then since it's a liquid, it can move because the liquid molecule moves, but I would still call it an insulator. Yeah, yeah. So it gets more complicated with fluids because you can have charges moving in an insulating fluid because the molecules moved, which is why we talk about solids first. Yeah, yeah, yeah. Keeping it simple. But again, the whole point here of this hour is just to get that mental picture. What is happening on a microscopic level? So I hope you saw that what really happened here at first is I touched it and made the negatives jump onto what I would say here, the left-hand side of my pit ball, my cork ball, cylinder. It's actually cork and cylinder, so it's not even a pit ball, but cork cylinder. But you'll notice something else I said. I said for this, it didn't stay here. What happened to these negatives? And the reason I drew some on the right-hand side is some of these negatives will migrate over and spread out along that pit ball. Why? Because they can flow. It's made out of aluminum. And aluminum and all your metals are conductors. And so again, as you do the lab and as you do our discussions and as we calculate it, we're going to want to classify these things as insulators versus conductors. And what we mean by a conductor is the electrons can move. So when you put a bunch of electrons right next to each other, remember what we said earlier, that negatives repel each other. So would all of these electrons stay on one side of the ball? Well, they're all repelling each other. So if they can move, they will. Now, in the vinyl, when you had a bunch of negatives near each other, they were pushing, but could they move? No, so they stayed next to each other. And so the difference, again, between an insulator and a conductor goes down to can they or can they not move? They always are pushing on each other. But this table, if I push on it, it doesn't move. If I'm an electron and it's an electron, we push on each other, but neither one of us move. If it's a conductor, like this table, it moves. And when I push on that, it goes somewhere else, and they spread out over the whole object. And so that's why my mental picture is a little different here for the conductor as here for the insulator.
So if you were to scrape off electrons off one side, then electrons from around there would come in and fill the spots?
This one here?
Yeah.
Okay.
And maybe it charge somewhat?
Yeah, yeah. So if I did, and actually I will in a second, his question, for those of you who may not have completely heard it, he said, what if I started neutral, I think, and I scraped electrons off, so there's missing some. These still have a lot of electrons, so they'll flow over, and so the positive will be all the way around the ball. Not that the positives moved, but that the negatives moved and have now an equal distribution of positives on that pit ball. Yes. And so again, good point. But also notice I explained it with the negatives moving, not the positives. Yeah.
So when you transfer the electrons from the vinyl to the pit ball, is that induction versus conduction?
Oh, at this point, I would call this charging by touching or transfer. And what you've seen so far, I would call the other option charging by rubbing. Okay? And what I'm going to do here is show you a bunch of things. And when we're finally done in this hour, then I'm going to write a bunch of words on the board. Inductor, capacitor, transfer.
No, it doesn't negate it charging, it just mitigates the amount it does. Right?
Are you back to this part?
Yeah, yeah. Because you're still, overall, you're losing electrons if you're rubbing them off.
Well,
It's just you're mitigating the amount that you're charging it.
Okay, let me actually do what you're asking. This is what you're asking. You're asking to get this ball positive as opposed to what I did here, negative. Now, I can't do that. And so I'm going to come over here, and here's my pit ball, which a moment ago I charged negative. And it still might be negative, maybe not sure. How can I get rid of these negatives before I even begin the experiment you're asking? What if I touched it? What would happen here?
The moisture in your hand will spread away.
I'm a conductor too. And so when I touch this, these electrons on here, which again, remember, all the electrons are pushing each other. If I were to touch a piece of vinyl right here, all I would do is take off the electrons where my fingers are touching. Would I take off the electrons that are here? No, because they can't move through the material to my hand. This is an insulator. But here, it doesn't matter where I touch it. Even the electrons on the bottom will do what? They can flow through the aluminum to my hand, on my hand, over my skin, down my arm. They probably get stopped with my shoes because I've got some rubber sole shoes on, but they can flow all over my body. And I will claim that almost, if not completely, neutralizes this, because again, these are all negatives. So they want to get as far away from each other as possible. So something that is much bigger, and I am much bigger than this little pit ball, are going to want to go onto me. Because if there was only, say, 4 electrons on here, they've got to be pretty close together. You put 4 electrons on me, 1, 2, 3, 4, they spread out in a greater distance, and they want to repel each other. So, before I begin your experiment, I'm going to show you something called neutralizing. If I want to neutralize something, just touch it with a bigger object. How can I neutralize me now? Touch a bigger object. What's a bigger object?
Yeah, a bigger conductor object.
Good point. A big conducting object. Yes, good point. All right, so, and there's a big word here I want you to get at. What's the biggest object that conducts I can find? The Earth. And so don't be surprised, you probably heard it before, we ground a lot of our electronics to keep them from building up charge. So I am going to touch the Earth in the easiest way I can, which is this metal pipe. This plumbing comes up, it's all buried in the ground, those electrons will come off to me, they will conduct onto the pipe, they will conduct to the ground, they will spread out between here and China and say, okay, now they're far apart. Right? And so that's why we use that phrase, grounding. That's why grounding is a safety device. And you'll see that as we get into our electronics. Yeah.
So by grounding, electrons move into the Earth, but if you're like positively charged, will it take electrons from the Earth into you?
Exactly. Yes. Yeah. No, it would be exactly the opposite. Okay, so now I can do your second part of this experiment. And that's what I want to spend the balance of this time, just showing you a bunch of different things. And if they make sense to you, then you're ready to do an infinite number of problems. Yeah.
And how does this use static bands work to make sure things don't multiply? Like the static bands and
Oh, when you're working with electronics, the static band is to get the charge off of you.
Yeah.
So you don't transfer it to that little device you're working with.
How do they work?
Oh, exactly. It's a conducting band. Okay. Yeah, and so the conducting band is on my arm, and it's onto the ground. So if I am working with something, or if I shuffle my feet, then the charge that would have built up because I'm shuffling my feet, which I should have used as a good example, you saw me building up charge by rubbing it. I bet when you were a kid, you would probably go barefoot or with socks and rub the carpet and shock your younger siblings, right? And so the same idea is that static band is now connected, and so anytime I rub my feet and the charge would have built up, it conducts off of me and down to ground. And that way, when I go to touch my electronics, I don't shock it and destroy it. It doesn't take too many electrons to destroy modern, small microchips. So it's real important, yeah, you have those static bands on you.
What is a shock? What happens with the electrons?
A shock really is then a transfer of electrons from one to another. So I actually had a shock right here. Although I suppose some people might say a shock is more extreme than just the simple touching of them, but it's just a large amount. Yeah, yeah. So that you can hear it and see it and feel it. All right. Okay, so now finally getting on to this one here, I wanted you to see I am now grounding it. So that is now neutral. If I come over here and find my paper that I've been rubbing, if I were to rub it, and again, which one is the positive? The acetate, the clear one. All right, so I'm going to take the acetate. I am going to rub it. I'm going to pinch it hard and encourage you to do the same thing tomorrow in lab. Rub, 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 rub real hard. Get it till it's warm, okay? And if I touch it, and this one you might have to do a few times. I did the vinyl first because the vinyl, well, I got a little bit. Can you see it? Touch it a second time. Maybe that's enough. Should I do it a third time, or can you see it? Okay, and so again, this will be your challenge tomorrow to play with it and get enough charge on there. But as you can see, it is repelling. And why is it repelling? What happened on a microscopic level? Well, as you correctly pointed out, I first was rubbing the acetate with the paper. That tore the electrons off of the acetate. The acetate was now positive. I then brought the acetate near the pith ball, and when they touched, now notice it's touched because the air is an insulator, but when they actually touch here, this object, which is neutral, and this was an important statement I made about a half hour ago, are there any charges on a neutral object? Yes, there's an equal number of positives and negatives. Are there any negatives on here? Yes, and so these negatives, or at least some of them, and so I'll draw positive, negative, positive, negative, positive, negative. Or maybe I'll do 4 sets, positive, negative. And on the other side, I will do another 4 sets. But as you pointed out, what's going to happen when I touch them is this negative will go to there, this negative will go to there, this negative will go to there. And now this will be neutralized. It's the whole reason I moved my hand back and I rubbed the acetate again before I brought it back, so that this would now be positive because the negatives went over here on the paper. But if I continue on with my picture, as you pointed out, I would now have a bunch of positives with equal positives and negatives on the other side. But because this is a conductor, something different happens than the insulator. In the insulator, when I took off the positive and neutralized it here, the positives remained here. Or I should say the negatives did not move up to there. And that's the difference here. On this one, some, not all, of the negatives will transfer over, and so the end result is that I have a pith ball that is now positive because I took negatives off of it because I touched it with a positive object, and that the positive charge is distributed all the way around it because of the conducting property of it. Yeah.
So, to neutralize or ground something, you need something to be electrically charged so you can actually ground it. Because if it's positively charged, you need to be carrying enough electrons in your body to touch it and make it neutral, right?
Right, and okay, and so this is positive right now. If I were to come along, I would still say this neutralizes it. It needs 4 electrons from me. But an object that is much, much bigger can easily supply those, because now I'm missing those 4 electrons, but they're on far parts of my body, and that is electrically happier, if you will, because they are far apart from each other than when they were 4 close together.
Is it more like difficult to neutralize something when it's positively charged than when it is negatively charged?
No, they just flow one. What really makes it the most neutral is really how many times bigger am I than it? Because the truth is that the last electron doesn't want to come off. It has no reason. Or the last positive on here doesn't want to suck an electron off of here. It really has no reason. So it's really a proportion. How much bigger am I compared to it? And so in this case, I am many times bigger than it. So we roughly say it's neutral. It's such a small. And the Earth is much bigger than me. So when I touch the Earth, I can say I'm pretty much neutral.
In the lab, can we, if it's like insulators, can we just use one side to touch it and then just flip it over to the back side and it'll still be...
Sure, if that works. But what you're going to discover is you're going to have to rub it hard. And hopefully I'm making it look easy. But it'll be the first time you do it. And I know the tricks. All right? And so our weather conditions are looking real promising, so I think we're going to get some great results tomorrow. But there's been many times where I have to walk around and kind of show people, okay, you're not rubbing hard enough. So I'm just trying to give a gentle, you're right, you can flip it over, and if you get your results, that's good. But I just encourage people, bring it back, rub. If that's not enough, bring it back, rub. If that's not enough, bring it back, rub. That's not, you know, and just keep doing it. Okay? Yeah? Hold on that question for just a little bit, okay? All right, let me show you a couple more things here. All right? Now, one of you pointed this out already, and at the very beginning, I was looking for my rag. Oh well, I think this is still erasing enough. But I like that little towel. It erases a little better. Did you guys notice something momentarily before I actually touched it? I mean, I asked you to focus on, watch it when I touch, and then come back. And then, in this case, they were both negative, so they repelled. In this case, they were both positive, so they repelled. But did you catch this? Maybe I'll grab another piece of paper here. Let's go back to the vinyl. Did you notice when I rubbed it? And before I got a chance to touch it, did you see anything else? Oh, neutral. Let me start neutral. Okay. Neutral. Negative object. Right before I touch it. Oh, try it again. I don't see it either. Okay. All right, rub, 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 rub. Right before. Oh, here we go. See anything? Did you see how it was attracted over? Then it touched, which then it transferred charge and it became negative, and then it repelled, which was what you were pointing out earlier. Okay? Why did that happen? Yeah, and a fancy word here is dipole. Right before I touch it, let's draw a picture here. If I take a negative and I take this pith ball, or like I said, it's really a cork cylinder, I just can't say that, but this pith ball, and it's neutral right here before I touch it, what's going on here?
Pushes the electrons to the other side.
Is this thing positively charged?
No, it's not.
No, it's not positively charged. But, as you're pointing out here, what would happen to the electrons that are in here as they get close to those negatives? Right. So I'm going to represent that by putting a bunch of negatives on the right-hand side. Those negatives will actually move. Now, of course, if they move away, what does that say about the left-hand side? It's positive. So I would say at this point, the pith ball is still neutral. Although it's neutral, meaning it has an equal number of positives and negatives on the whole thing, the charges are now separated from each other. And so this is what we're going to refer to as a dipole. When you have something that is actually neutral, it is but separated. The total charge of the object is neutral, but the object itself is polarized. It has created a dipole.
And that needs to be a conductor.
The way I have described it so far, it has to be a conductor, okay? But something similar to this would happen even for an insulator. We'll see that in chapter 26. So that's not really a very good yes-no answer, because it is not, it would work for an insulator too, but for a different reason. Okay, and so remind me in chapter 26. But it's easier to explain it with the conductor and start there, and so that's why we're in chapter 23. Yeah?
If they were both conductors, would they not have that initial attractiveness?
No, you would still have an initial attraction even if it was an insulator. Just the explanation and the mechanism is different. So I'm going to put that off till chapter 26 and just say the conductor part of it separates it, and we will get it. But I want to make sure I'm not saying no to that question. But at the same time, it's more complicated, and we need to learn a few more things before we answer that one. But insulators will still be attracted over, yeah.
So all this moving electrons and stuff like this, can a battery produce a similar effect, because the anode of the battery pushes out electrons and the cathode pulls electrons?
Exactly.
So is it possible to have a static charge on a metal plate that you just don't connect it to each other, but just put the wires in it? Can you get a static effect that way?
Yep, that's exactly what chapter 26 is about, called capacitors. And you'll see lots of it. Got a great lab on it. Just don't electrocute yourself. No, I'm just kidding. Our labs will be safe. We make them what Don likes to call idiot-proof. You can't electrocute yourself or break the material. Now that doesn't mean don't try, okay, to break it. Because I bet if you tried, you could probably damage itself or yourself. But it's all designed to be, and I'll explain those in the lab. All right, but as you guys hopefully saw here, once you have this separation, and maybe it'll be better to even color code it a little bit here, what happened before I actually made contact then is this part of it, the left-hand side, was attracted the right-hand side was repelled. But I'm going to claim that those two forces are not the same. I would say the blue one is a little stronger. Why? Yeah, and I didn't say it, but hopefully you were probably noticing that the amount of interaction depends on how close I am. And so even though this pith ball is neutral, and even though there is both an attraction and a repulsion, the attraction is a hair more, and you do get that little attractional piece, even though the pith ball was neutral. So I think a more complicated one to understand is a charged negative vinyl strip and neutral end up attracting until they touch, and the charge transfers over, and then they repel. And that's what you saw. And you will see tomorrow as you play with it. It's kind of fun. Yeah.
Is it safe to say that dipoles are only created on conductive material?
No. Again, that same question. I can have a dipole on an insulator also. It's just a little different. And so we're going to wait till we get to chapter 26 to talk about that one. But right now, I will say, yes for now. Yes for now, yeah.
Just going over the edge here a little bit. The direction of the force on the one to the left, shouldn't it be like going to the right?
Well, these are opposite. These are.
So not transferring.
Okay, fair enough. But don't confuse what my diagram is showing. What you are saying is correct, but you are saying what is getting pushed to the other side are electrons. Okay, so the electrons actually go over to here. Okay? The nucleus is still here from the electron that left. So on the nucleus, there is a pole that way. The nucleus is positive. And that's what I'm trying to represent in this diagram. That there is a pole on the nucleus, which is part of the object. So the part of the object is pulled that way. Now, the pushing away is on the electrons. And the electrons are part of the object too. So there's also a pushing away. So that's why we have both a attraction and a repulsion going on. The repulsion is on the electrons, the attraction is on the nucleus. But this is a little bit bigger than that, and that's why we get a net attraction until we then swamp this with so many more negatives that the negative become, the force pushing it away becomes greater than the attraction, and then it pushes away. And so that was the mechanism. And what about the other way around? I showed you the case where I started with a neutral pit ball and a negative strip. What do you think would happen in the opposite? What if I neutralize the pit ball, take my paper, take my acetate, and rub it? When I get close, will there be any interaction? Will it attract it at first or repel it? It will attract. Oh, I'll show you first, and then we'll see if we can draw a picture of it. And then, like I said, the acetate's a little bit harder to see. But if I get it close, hopefully you'll first see a little bit of attraction right there, and then the touch, and then a repulsion. Why? Well, again, what's going to happen to these electrons in the conductor? We're talking about conductors. Insulators are coming up, right? But what would happen to the electrons here? Yeah, they would move to the left-hand side, leaving the nucleus on the right-hand side. Again, a little color coding here, but I'm going to have then an interaction of these negatives over to those positives, so that's an attraction. I'm also going to have an interaction of the nucleus to these positives, and that's going to be repelling it. And so again, we get both an attraction and a repulsion, but they're not equal. Which one's bigger? Yeah, the attraction. Why? Because it's closer, and I know we haven't done any numbers yet, but we're getting close. We can get our calculus out here in just a second. Or I guess first it'll be arithmetic, then it'll be calculus. But what we're going to have here is attraction, and I think you saw that, right? How about I switch it up a little bit? Let me grab this device. This is what we're going to call an electroscope. Now I like this one because it's big for the class to see, but it doesn't work well. So let's see what happens. If it doesn't work well,
What is it supposed to do?
I'm going to switch to this one. Okay, this one is the one you will be using in lab. It's small, and you can look at it, and it's extremely sensitive and accurate. Okay, and so tomorrow in lab you will see this one, or Thursday if you have it on Thursday. But let's see if we can look at this one. Let's study it closely. Here's what I want you to notice. I want you to notice that it is made out of metal, aluminum in this case, with parts of it that can move. And the part that can move, we call it a movable leaf. I'm not sure you would really call it a leaf, but when you get yours and you see the foil does look like a leaf, so you'll understand the name a little bit better. But that gold colored one right in there, I don't know if you guys can see it move, but that's the equivalent of this one here, okay? It can move. Now the other part of it is a thicker metal, and it can't move unless I really bend it. So this I will call a non-movable leaf, and this I will call a movable leaf. In addition to that, I want you to notice, and I don't know if you can even see it, but that metal piece extends up to here. And so this top part is called the knob. But what's real important here is that you recognize that the whole thing is made out of metal, and it goes up through, and the metal here is connected to the metal here, and the metal is a conductor. Now, if you look closely, it looks like there's a piece of plastic here. That's because wrapped on the outside is a piece of plastic, meaning that the electrons that are on these fixed and movable leaves can go up to the knob, but they can't go on this metal ring on the outside. Okay? So none of the electrons in here can get on this ring. And none of the ones on this ring can get into here. But electrons could move from the fixed leaf to the movable leaf. They could also go up to the knob or down from the knob. Okay, so with that in mind, see if this makes any sense. I will take a piece of paper. I will take a piece of vinyl. I will rub it. I'll rub it a lot. I will bring it close to the knob. I won't touch the knob, just close. Do I see anything? I will pull it away from the knob. Do I see anything? What happened here and why? Did the electron transfer to the leaf? All right, good. Notice I didn't touch it. Remember we said the air is an insulator. So did any of the electrons that were in this piece of vinyl go onto my electroscope? Yeah, unlikely that any of them transferred. So you did notice something though. What did you notice? Did you see that movable leaf move out? Why? Yeah, and hopefully you mentally see this. I brought the negative near it. I didn't actually touch it, so I didn't transfer any negatives onto the electroscope. But just like we talked earlier with this pit ball, when you bring the negatives near this knob, what happens to the negatives that are in the knob? They move down. That was the key for me to say that this was made out of a conducting material. And they move down. And so I will represent that by putting negatives down here. Of course, they left the knob, so the knob is lacking electrons, and they are positive. And so we would say the electroscope then has been polarized. It is a dipole, if you will. We have an equal number of negatives near the bottom as we do positives near the top. The whole electroscope is neutral. However, look at the charge between the two leaves, the fixed and the movable. What are those? They are negative, so what will happen to them? They will repel. And that's what you were seeing. You were seeing this repel out. And then you saw something even better. What happened when I removed that negative strip from the top? Right, there was no reason these guys want to stay down here anymore. There's nothing pushing them away. In fact, just the opposite. The fact that they are missing from their nucleus, and the nucleus is positive, the nucleus is trying to suck them back up. So as soon as I moved it away, these negatives moved back up and neutralized the top, and we were back to the place we started before. An uncharged electroscope with gravity pulling the leaf together. And they moved out only because my little charges were stronger than the gravitational force. Well, what if I extend on that a little bit? What if I take my piece of paper? What if I take my vinyl? And again, rub it. And this is where this one has a little trouble. Let's see what happens. And I touch it this time. And I'll not just touch it, I will touch and swipe. Because remember, they can't conduct off of here. They can only come off where I touch it. So the swiping touches it here, 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 here. So what happens to the negatives that were on here? They transfer onto the electroscope. So what are you seeing now? Yeah, you are seeing the leaves move out and they stay there. I am going to touch it, but before, I'll try the paper since you asked. But how can I make the leaves collapse? And there they go. And there they go. Right? And so I actually put them on. And so if I was drawing a picture of this scenario, it would be different. I would first pile on a bunch of negatives onto the knob because that's where I actually touched it. But because it's a conductor, they don't stay there. They're all moving around and they spread out over the object. And of course, we have then a negative and negative objects. They spread out, and of course they repel. And they remained that way, even though I took the strip away. And the only time the leaf collapsed was when I came back and I touched it with my finger. What the heck does a finger look like? Oh, geez, finger. Yeah, there we go. All right. So I touch it with my finger, and I pull those electrons off, and the electrons went on to me, right? And that's how they came off. I could have also taken them off by touching it with a positive object, which, Danny, was your point with the paper. But let me just switch that a little bit different. Let me charge it negative again. Swipe. Is that going to be enough? Maybe just as well. What if I touch it then with a positive? Yeah. So as I touch it with a positive, it should be neutralizing this. I didn't even touch it. No way. And I bet not a surprise. What happened there? Yeah, see, I may have touched it with more positive or the negative. I don't really know how much I did. And that's what I wanted you to see. Let's go through this again here. Let me neutralize it. Okay? And start with a negatively charged electroscope. I charge it. I swipe. I'll do both sides. And right now I should have some negatives on there. Right? The leaves are sticking out here. And so this is the picture I have without my finger on it. I've got that whole thing negative. But what I wanted you to see, and I think I did catch your attention, what do you see before I actually even touch it? What happens here? Oh. I didn't see it. Uh-oh. I think the leaf, it looked like it fell out of its little socket there. Let me try it again here. Okay, so if I touch and swipe, that should be negative. Now I'm going to be at the positive, and I'm going to bring it near. Bring it near. Bring it near. I'm not actually touching it. Bring it near. Bring it near. What's happening now?
They're moving up.
Exactly. I am bringing a positive nearby. That positive will draw the negatives up. Negative, negative, negative. And that means the negatives are not on the leaf. Okay, they're not on the leaf, then gravity pulls the leaves back together and the leaf collapses back down here. And so there's a lot, how are we doing on time? Oh, there's a lot of different combinations we can have. But make sure I show you all. Let me jump to another one. I can do the same thing with positives, but I'll skip that one. Let's try this for a second here. I'll neutralize it again. I think the hardest one to understand is this last one here. Take my paper, a little better paper. I'll take the vinyl. I'm going to rub it. Now this much you already saw. If I bring it close, the leaf moves out, right? What if I put my finger on it and move it close?
The excess electrons are moving into your body.
Right. So what I want you to see here is the electrons, as they get chased off the knob, aren't going down to the leaf.
Going to your body.
They're going onto my body. See, if my finger wasn't on there, they would go down to the leaf.
Here's an idea. Put your finger on there, or very close to your finger.
And so here's the whole story. I'm going to put my finger on it. I'm going to bring it close. I'm going to take my finger off and pull it away. Never touched it with this. I touch it with my finger. It obviously is charged. Is it charged positive or negative, and why?
Positive.
Yeah, why is it positive? Exactly. So you guys don't even need to show you a second time. You got the idea that by putting my finger on it here, these negatives go onto my body, making the knob positive, but not going down to the leaf, so the leaf doesn't stick out. Once I pull my finger off, the negatives are now trapped on my body, which means I'm lacking the negatives on the electroscope. The knob is positive. Once I pull the strip away, what happens to down here? Right, negatives down here at the bottom race up here to kind of neutralize the knob, leaving the bottom positive. And so this electroscope does get charged. And interesting enough, it gets charged positive, yet I was using a negative object. Because what I really did was to use the negative object to chase the negatives onto me. So the electroscope is lacking negatives. To convince you that this is actually positive in charge, I am going to take a negative and put it close by. Because when I put a negative close by, what does negatives do to the negatives in the knob? Pushes them down. If it pushes them down and that neutralizes it, oops, too much. If that neutralizes it, closer, closer, don't get stuck. Oh, darn, stuck again. And this is why this one, that little, it's kind of, anyways, I guess it, can you see it go down a little bit? It's kind of getting stuck on its axle, but it goes down, there it goes. Down there. If I get too close, it starts to go out again. Why? Right, because then I have pulled up, I'm pushing down negatives. I have pushed down so many negatives at first that I neutralize it. That's why it collapses. But if I get even closer, then I can put even more negatives down there. And now the leaves start repelling because they are negatives down there. And it's hard to tell when they're repelling, if they're repelling because they're both negative or if they're repelling because they're both positives. That's a difficult one. Now, I really didn't save enough time, bummer, but I did want you to see kind of a fun one to do here is this one here. I've been keeping it warm, hopefully keeping the water away from it, but you have watched me the whole lecture rubbing materials with my hand. I can only rub so hard. If I get something more mechanically driven, and so there's a little electric motor down here, and I don't know if you can see there's even a little belt, but it's going to turn a belt and do the rubbing for me. Most of the rubbing I am going to be interested in is going to take place up here at the top. Here's the top of that belt, and it's rubbing against these little metal filings. But what happens as it rubs, it takes electrons off of the metal and puts them on the rubber. Remember the rubber from the Ben Franklin one we said an hour ago loves to suck up the negatives. So this metal ball here at the top should get fairly positive, much more positive than I could do by me rubbing it. And so I'll give it a second to get enough rubbing going on. And then I will say put this on here. And that should suck the electrons off of the tissue paper. And of course now all the tissue paper is positive in charge, and that should make them all positive and they repel. Another fun one to watch is, and actually let me neutralize it for just a second. So I've got this ball hooked to this wire, which is actually hooked to that wire, which is plugged into the wiring, which is hooked to the ground. That's why that third plug is called the ground, because that third wire goes through our building, and at the other end of our building there's a copper pipe buried about 20 feet into the ground. And so I'm going to ground it. Okay, that should neutralize it. I am going to put pieces of paper. I am going to let the paper get positively charged, and they should repel. Same thing should happen with these pie pans. We're out of time today, but I want you to notice one at a time. They didn't all get charged and send away in one big shot. There's something important there that we have yet to see here, but obviously they repelled, so you'll see more on this. And since we are at it, oh, we have 5 minutes, right? Oh, good. Maybe you could actually see, somebody asked about it earlier, a spark. Again, this is the transfer. If that is very positive, it will suck the negatives out of the top of this ball, and you can probably even see them, probably better with the lights off. And although we still got the windows open and whatnot, but you can hopefully then actually see, well, maybe not. Yeah, not very well today. Yeah, building up a little bit. And I probably, Thursday, remind me to do this at the beginning so that it's nice and dry. I'll dry it before class. Oh, here's a good one on this backside. And then there's a good one. Or, for those of you who are exiting class, it's always fun to do it to yourself. Ah, there it goes. And so you'll get the little zap, and you can fill it. And better still, each zap sucking the electrons off of me. And so all the little pieces of the hair on my body are doing that. I don't have any on my head to show you. But on here, it will suck it off there. All right, well, we'll stop there and get into the math on Thursday.
What do we do for waitlist ad codes?
Oh, yeah, follow me. I'll have to give you ad code. Yeah. Yes. And let me remind you about the 199W class and the ad codes up here.
So Mike, sign up with you on a Thursday lab, but is it okay if I change it to the Wednesday lab?
Probably, I'd say don't do anything yet. I mean, everything's full and closed. Yeah. It might accidentally bump you out.
Yeah, I'm not going to drop.
Yeah. So
is it okay if I just come in tomorrow morning at your 8 o'clock one and crash it?
Yeah, Don's doing it actually. Yes,
okay.
Yeah.
Awesome.
Yeah, and that's the small one. So yeah.
Okay.
Yeah.
So Dr. McKay.
In fact, I'm going to encourage people to do that to try and balance the numbers. Yeah.